Welcome to our next speaker and our final talk of the day from Trey Hunner. Trey helps developers understand Python and writes a series called Python Morsels. Please reach out to Trey for help everything Python related. And without further ado, Trey, the floor is yours.
Thanks, John. So, my name is Trey, and I help Python developers level up their Python skills. I do that through team trainings on both introductory and advanced topics, and through Python Morsels, which involves deepening your skills through hands-on Python practice. I also share a Python tip every Wednesday morning through my newsletter. This talk is about mental models, specifically the mental models that we use when thinking about Python's variables and objects. When our mental models don't match up with how Python actually works, we run into gotchas. We're going to start by looking at 5 gotchas. If we make a first list and assign second to first, when we change first by appending to it, second also changes. But if instead we had changed first by assigning to it, second doesn't change. Changing first doesn't always change second. That's gotcha number 1. Let's say we write a function to square all numbers in a list. If we make a list of numbers and we call our square all function with this list, it will return the squares of all the given numbers, which is what we'd expect. But the original list was also modified, which might upset a caller of this function. That's gotcha number 2. Let's say we use nested self-concatenation to make a list of lists. We multiply a list containing 0 by 3, and then we wrap that in another list that we multiply by 3. We end up with a list of 3 lists, each containing 3 zeros. If we assign 9 to matrix 1, 1, we'll change the middle element of the middle list. Sort of. We actually end up changing all 3 of those lists. That's gotcha number 3. Number 4, let's say we have a list of colors that we'd like to be keys in a dictionary. So we use the dictionary from keys method to create a dictionary of lists. If we then add the string duck to one of these lists, every list in this dictionary changes. We tried to change one list, we ended up changing all of them. Let's say we make a to-do list class with an initializer method that accepts an optional tasks list. The given tasks list is stored as a tasks attribute on each to-do list object. So if we create a new to-do list object, and two new to-do list objects rather, and we append a new task to the task attribute of the first one, the second object's tasks attribute will also change. So we tried to change the tasks for Monday. We actually changed the tasks for both Monday and Tuesday. So that's our last gotcha. My goal in this talk is to clarify these 5 bits of code. We'll do that by considering the mental models that we use when we think about Python's variables and objects. If you think of variables as like buckets that contain objects, then when we assign a variable to an empty list, that variable would contain that list. If we then assigned another variable to the first one, the list would be copied into a new bucket. But if we then append 9 to our second list, that would change the list. Now, at this point, the first list shouldn't change, but in Python it does change. In Python, this mental model of variables as buckets that contain objects doesn't work. Variables in Python are not buckets that contain objects, and assignment statements don't copy anything. In Python, variables live in variable land and objects live in object land. So we have 2 different places where variables live, or where variables and objects live. When we assign a variable, we draw an arrow from the variable to the object. Then when we assign another variable to the first one, we draw another arrow from the second variable to the exact same object. So when we modify our second list, the second list changes. But so does the first list, because they're the same list. This is the mental model that I usually recommend for thinking about how Python's variables and objects work. I call this the pointers mental model, because it looks like variables point to objects. But some of you are probably thinking that word pointer has a meaning, right? It has a technical meaning. It's not just about pointing in English. Pointer is a technical term that has a specific meaning. Python's pointers are not like pointers in low-level languages like C and C++, at least not quite. There's no dereferencing pointers, there's no pointer arithmetic, they're not nearly as scary or as powerful as pointers in C or C++. The Python documentation actually doesn't use the word pointer, though. It refers to variables as bindings, though it also sometimes calls them references. I usually prefer the word pointer, though, because it makes me think of an arrow pointing from a variable to an object, and I find that visual helpful. Let's talk about the word change. Earlier I said if we change first by appending, second changes. But if we change first by assigning, second doesn't change. The word change is the problem here. There are two different types of change in Python. Assignments change variables, and mutations change objects. We can use our pointers mental model to help us differentiate these two types of change. When we append to first, we are mutating the object that first points to. Since second points to the same object, accessing second will show the same changed object. But when we reassign first, we're changing which object first points to. But that doesn't change second at all. Second still points to the same object as before. Mutations change objects. Assignments change which object a variable points to. So variables in Python don't contain objects. They point to them. Because of this indirection between variables and objects, there are two distinct types of change: mutations and assignments. Mutations change objects, and assignments change variables. Which means the phrase, "we changed x," is a bit ambiguous. Do we mean that we changed the variable or the object? Is it the variable x itself or the object that x is pointing to? In other words, did we do an assignment or a mutation? So that explains our first gotcha. When we point two variables to the same mutable object, changing the object through one variable changes it for both. So if you can change the object, pointing two variables to it is a liability. In Python, we have two different types of change, but we also have two different ways to ask the question, are they the same? We have the double equals operator for equality, and we have the is operator for identity. You can think of equality and identity as asking about model numbers and serial numbers. Model numbers help you identify equivalent objects. Serial numbers uniquely identify a specific object. Equality asks about whether two objects represent the same thing. That's like a model number. Identity asks whether they are the exact same object. That's a serial number. If we ask whether first and second are equal, we're asking whether the objects represent the same thing. If we ask whether they are identical, we're asking whether they point to the same object, whether the variables point to the same object. Unlike identity, equality doesn't ask the objects anything. It just checks whether two references point to the same place. So equality compares values, identity compares references. The is operator is very rarely used in Python outside of comparisons to none. When we ask, are they the same, we usually want the double equals operator. We usually want equality. Checking equality is much more common in Python than checking identity. But identity can be handy when you're debugging. If you suspect that two variables point to the same object, the is operator will tell you whether they do. So assignments change which object a variable points to, and this is what an assignment looks like. But it's not the only way an assignment might look. Import statements also assign to a variable. Each iteration of a for loop assigns to a variable. Function definitions assign to a variable. Class definitions assign to a variable. We've just assigned to the variable e 5 times. Any Python feature that updates a name, updates what that name points to, is some sort of assignment. It is performing an assignment. In fact, passing arguments to a function is also a form of assignment. So when we called the square all function with a list of numbers, the local numbers variable within the square all function was assigned to the list object that we passed into that function. When we then mutated the numbers list by updating each of its indexes as we looped over it, we were mutating the original numbers list. That's why our numbers list outside the function changed. Function arguments are just variables, and all variables point to objects. Variable assignments don't copy objects, and neither do function calls. This is the reason that in Python, functions rarely mutate the objects that are passed into them. Some functions, like the list append method, are designed to mutate. That is their purpose. But in general, it's very common to build up new lists out of old lists, with a for loop, or with a comprehension, or with the many other Python features that exist for making new objects out of old objects. There's a lot of them. Most of the time, your function should return new objects instead of modifying existing objects. But wait, this assignment statement mutates the list. So is it an assignment or a mutation? Well, it's both. Assigning to a list index mutates the list, just as assigning to an attribute on an object mutates the object that that attribute lives on. In fact, if you squint hard enough, every assignment in Python is kind of a mutation of some sort of namespace. You may not be able to get your hands on that namespace, but it has to change something somewhere. So assignments can mutate an object. Some of them, at least. So function arguments are just variables and no objects are copied when a function is called, just like an assignment, which explains our square all gotcha. So 3 more gotchas to go. We've talked at this point about variables. We haven't really talked much about objects, though. So let's talk about data structures. Data structures don't contain data, depending on what we mean by data. What I really mean by this kind of absurd-sounding statement is that data structures don't contain objects. Earlier, I showed you a diagram that looked like this. Because we assigned 2 variables to the same value, both first and second point to the same list, and that list contains the number 9. But that list doesn't actually contain the number 9. This diagram should technically look more like this. A list in Python cannot contain the number 9. It can only contain a reference to the number 9, or a pointer to the number 9. Variables can only point to objects, but objects can also only point to objects. Objects can't actually contain other objects, which is why if we put our list inside another list, the new list won't actually contain our list. The new list's first index just points to the original list, which means phrases like a list of lists are actually a shorthand for a list that contains references to lists. Also, the word containment is a bit misleading, because objects in Python cannot contain other objects. They can only contain references to objects. So when we ask whether one object contains another, we're actually asking whether one object contains a reference to an object that is equal to another object. But instead of all that, we just say y contains x, because it's easier. So containment's sort of a lie, but it's also sort of a useful lie. Let's revisit our last three gotchas, starting with our list of lists problem, where we used self-concatenation to build up a 3x3 list of lists. We multiplied the inner list by 3, which creates a list that points to 0 3 times. We then multiplied the outer list by 3, which creates a list that points to the inner list 3 times. So we end up with an outer list that has 3 references pointing to the same inner list. Concatenating a list to itself with multiplication doesn't copy objects in that list. So when we modify one of our rows, we're modifying the one object that all 3 indices point to. Index 1 in the inner list now points to the number 9 instead of the number 0. But since all 3 outer indexes point to the same inner list object, all 3 rows show this change. They're all the same list. So don't use self-concatenation to build up a list of mutable objects. But how could we fix this? What could we do instead? Well, we could use a list comprehension. A list comprehension evaluates this 0 times 3 expression 1 time per iteration, creating 3 separate list objects. Using our oversimplified diagram from before we talked about the fact that objects can't contain objects, for the sake of simplicity, I want to show you the simplified one so the slide doesn't balloon out of control. We can see in this oversimplified diagram that each outer index points to a different inner list. Not the same inner list, but a different one this time, which means that when we mutate one of these rows, only that row changes, because each row is its own distinct list object. Changing one of them doesn't change the others. They're separate. So that explains our list of lists gotcha. Now let's look at our dict.fromKeys gotcha. Dict.fromKeys creates a dictionary with each key pointing to the same value. Here's what that looks like. All 3 keys in this dictionary point to the same list object. So when we append to one of them, we're mutating the one list that all 3 keys share. And that means that all keys show the same change, because they all point to the same object. So don't pass a mutable object as the default value to the dictionary from keys method. To fix this, we could also use a comprehension, though in this case a dictionary comprehension. This evaluates the empty list literal 1 time for each color in our list, creating 3 separate list objects. So the whole comprehension builds a dictionary where each key points to its own list. So when we append to one of them, only that one list changes, because each value is its own distinct list object. So that explains our dict.fromKeys gotcha. Now let's look at our last remaining gotcha, our to-do list class. When we create 2 instances of this class without passing a tasks list to them, what happens is that both instances' tasks attribute point to the same default list object. So when we append to one of them, we're mutating the one list that both instances share. And that means both instances show the same change. And in fact, we can actually look at the default value that's stored on the method itself and see that it changed as well. So Python reveals this to us if we want to look at it. So that empty list expression in our function definition was evaluated only one time when the function was defined, which means that that object, it was attached to the method, and mutating it through one of these instances actually mutated the original object. Now to fix this, one way to fix this at least, is we could use the list constructor to copy the default list. By using this list of tasks, we're copying the list each time we call our initializer method. So when we create 2 instances without passing a tasks list to them, each instance gets its own separate copy of that default list. The original default is still sitting on the method, untouched, still an empty list. So when we append to one of these, we're only mutating that one object's list. And the other object's list, it doesn't change, because each object has its own distinct list. But this also has another benefit. If we pass the same list into this class twice, each instance gets its own separate copy. So mutating the tasks list of one of these instances will not affect the tasks list of the other. Also, because the list constructor function in Python will loop over any iterable that we give to it and make a new list out of it, this class now accepts not just lists, but sets, generators, or any other iterable you can think up. Which is why classes in Python that are meant to change an iterable that's passed into them will often shallowly copy that iterable in their initializer methods. Often, not always. It depends on what that class is trying to do. Is it a wrapper or is it trying to make a copy? So that explains our last gotcha. All three of these last gotchas were due to the fact that objects in Python do not contain other objects. They only contain references to other objects or pointers to other objects. So if we end up with multiple references to the same mutable object, we might get ourselves into trouble. So a quick recap of what we've learned. Variables in Python do not contain objects. They contain pointers to objects. And assignments point a variable to an object. An assignment does not copy an object, which means pointing two variables to the same object is a problem if that object is mutable. But for numbers, strings, and other immutable objects, pointing two variables to the same value is fine, because you can't change the value anyway. Also, function arguments are just like every other variable. When you call a function, you are doing an assignment. So when you call a function, each argument that's passed in, it is just like an assignment in Python. It's just a pointer. Which means that function calls don't copy objects. So functions shouldn't mutate the objects that are passed into them unless that's their expected behavior. Instead, it's common for functions to copy passed-in objects either implicitly or explicitly. And objects can't contain other objects in Python. They can only contain pointers to other objects, which means if you store multiple references to the same mutable object, you might get yourself into trouble. So be careful when using utilities like dict.from keys that store references to a given object instead of copying that object. And when you're writing class initializer methods, be mindful of whether you're storing a reference to a passed-in object or making a copy of it. There's a time for each of those, and you want to make sure you're using the right one. Is it a reference or a copy? It's up to you. In summary, variables store references to objects, and objects can store references to other objects. But objects can't contain objects, and neither can variables. Also, function arguments are just variables, and so are attributes. But there are many odd corners of this topic that we didn't cover today for the sake of time, and you often don't need to know most of these things, honestly. We did not discuss variable scope in Python, which might seem like a big oversight, but mostly Python just has your back. It tries to do what makes sense when it comes to variable scope. We didn't discuss hashability. We didn't discuss optimizations that CPython does around numbers, strings, and tuples that people like to talk about and doesn't really matter most of the time. Arrays and direct value storage, and the fact that tuples can contain mutable objects, which seems like a gotcha, and it can be a gotcha at times. This URL is on the bottom of each slide in this talk. It contains links to resources that discuss some of these topics, as well as 2 great talks by other Python community members that I've been referencing for years. Before we wrap up, though, I do want to address a common question when I talk about this topic, especially for folks moving from other languages, or who haven't, thought about how and why Python works this way. Why does Python work this way? Wouldn't it be easier if variables and data structures contained objects and assignments copied objects? Well, imagine if every assignment made a copy of an object. Copying objects takes time and it takes memory. But also, how would we ever model parent-child relationships or any kind of relationship that involves storing a reference to an object instead of storing a copy of an object? We would probably need to make a distinction between assignments that copied and assignments that made a reference. Other programming languages have done that before, and that requires adding a different layer of complexity to the language. Python's way isn't necessarily the right way, but most days I really appreciate the trade-offs that Python made around this topic. Python's separation between variables and objects can definitely be confusing, but it's a pretty decent approach to a hard problem. Every decision has trade-offs, and everything is relative to its possible alternatives. Whether we are talking about a software feature or about politics, when we say this thing is bad, we should always ask ourselves, compared to what? We should acknowledge problems with the status quo, but we also need to think deeply and honestly about real-world outcomes. Thank you.